Hello everyone, welcome back again to my channel. My name is Harry Fargonando, and today we're going to talk about the Tech Talent Recommendation Engine. This is the project for the class of Advanced Machine Learning. Alright, what we're going to talk about, the first one is, of course, the machine learning from scratch, and second one is our pseudocode, and the third one is the implementation and experimentation, and the fourth one is the conclusions and feature works. As we know, this is the continuation of the previous videos, so we're going to deep dive again right now in our algorithm that we use in our previous videos. Alright, the number one is the machine learning from scratch, where we introduce our custom developed ML algorithm. Let's go back again. What's a recommendation system? Well, a recommendation system is an engine of filters and predict the most relevant items for a user based on the preferences. In our context of HR, it translates job matching candidates' profile with job requirements. And the engine learns from the data, which includes candidate skills, experience, and job descriptions. Well, as we know from our previous videos, we with the technique that we are using here is the matrix factorization techniques, a sophisticated approach to recommendation system which works by decomposing the candidate job matrix into factors. And these factors represent latent features of candidates and jobs, for example, skills and experience levels. And the goal is to find patterns that helps to predict a candidate's suitability for a role even with limited informations. As we know from our previous videos that the algorithm that we are going to learn here is are two algorithms: alternating least squares and gradient descent in matrix factorizations. All right, let's go back again. What is kind of matrix factorizations? Well, what we're going to see here is we have two factors, as you know. The first one is the you can see the user matrix, or well, in our case here is the a talent matrix, or the tech talent that we want to recommend to HR. And the second one is the skill matrix, or the technical skills that the talent must have in order to be recommended to the HR. Well, with times those two matrix, we do matrix multiplication, and after that we get this talent skills matrix, or in the picture is the user home matrix. Well, what are the components of learning that we have here? The first one is the model fitting. During the fitting process, the model optimizes a cost function, which is a quantifiable measure of error or loss. For our recommendation engine are the mean square error, or MSE, and mean absolute error, or MIE, are used as our cost functions. And the objective of this ML algorithm is to minimize the cost function. A lower MSE or MAE signifies that the recommendation engines made by the engine closely match the expected outcomes. And the parameter that we use here in our matrix factorizations are the latent factors for both talent and skills. And these factors are learned during the fitting process and represent the underlying attributes of technical skills. Well, how to optimize this algorithm? The ALS, or alternating least squares approach, optimize the model by alternately fixing one set of factors while solving the others, incorporating regular decisions to prevent overfitting. So yeah, we're fixing one set of factors while we're solving the other. So it's kind of like an iterative process. It might be computationally expensive, but well, it's just an ML from scratch, right? And the second one is the gradient descent approach, where we iteratively adjust the factors to minimize the error by moving in to the direction of the steepest descent of the cost function. Well, you might be wondering, like, how do we adjust the factors to minimize the error? Like, where do we start? Well, we start by choosing random data points. Well, maybe you're wondering, like, how do the code works? What's the math behind it? Well, we'll go deep dive of this and how to make the predictions. Once the model is optimized, it can make predictions. Or once the model have been fitted, you we can make predictions. The predict function computes a dot products between the talent factors and transpose of the skill factors, generating a matrix of predicted scores, indicating how well its talent matches the required skills. Well, this is the math behind our both of our algorithm. The first one is the alternating least squares, where as we know that we are doing matrix computations or matrix dot products. That's why we are times our the transpose of one of the a matrix and times the others. Like uh, the alternating least squares, the u are in this context is talent or the user, and the I is the item or on context is skills, and the PU and QI are the factors of the user's talent and the item skills to be solved. Where since we are doing this iteratively, it might takes a lot of time or maybe computationally quite expensive. And then since we are iterating from both sides of the factors, and the user rating factor are the RU, RE are the is the item rating factor, and the lambda is the regularization parameter, and the I is the identity matrix, and the gradient descent uh, which is the PUK is the user factor matrix, and the key QIK is the item factor matrix, and the EUI are the error for the user, and item I calculated as the error, where the RUI is the actual rating uh, minus the transpose factor or transpose matrix of the P or the user factor matrix times QI or the item factor matrix. That's why we got the error. And then we got the alpha as the learning rate, and the lambda is the regularization parameter. Well, how do our pseudocode works? Like this is where we outline the pseudocode that maps the core logic and the procedural steps of our algorithm. This is the first algorithm, the alternating least square in matrix factorization, where we first initialize the talent factors and the skill factors with random values. It doesn't matter what values that we will use here, as long as it we will go to our best points starting from those random values. And for each iterations, we fix, let's say the first one is the skill factors, we update the talent factors, and for each talent in talent factors we update the talent factors per talents using the regularized list squares on corresponding talent data. By the way, these regularized list squares can be adjusted again, or maybe well you can say like hyperparameter tune, and this is one of the parameters that we can tune over here. And that's the first loop, that's the first fix a matrix that we will find. And the second one is the for the talent factors we update the skill factors. For each skills in skill factors we update the factor skills per skills using the regularized least squares on corresponding skill data. And after that, from both of this loop we calculate the MSE and MA for the current factorizations and print the iteration, and we will see the MSE and MA how do our model works per training, like that. And there are the link for my code on my GitHub. All right, this is the gradient descent and matrix factorizations, where it's the same like the previous one, where we initialize talent factors and skill factors with random values. But this time, since we are not since we are not really fixing one factors and using the others to solve, and then we correctly or iteratively correct each other, this gradient descent is just using the random values and then choose the steepest step of error to correct the algorithm, the model, like that. So the this random values, this initialization with random values will result in, let's say, like unproducible model, since we are using random values and then training, and each training will results in different models, like that, unlike the previous one with the alternating least squares. Well, let's go back to our gradient descent, and for each epoch, for each talent in number of talent, for each skill in number of skills, if the rating exists more than zero, calculate the error as actual rating minus dot product of talent factor and skill factors, just like in our math in the gradient descent. And after the calculated error is well done, we update the talent factor per talent with gradient descent step, and the we update the skill factors with gradient descent step. Well, and outside of those loop, then we calculate the MSE and MAE for the current factorizations and print the epoch MSE and MAE. And there are also the link for the code of this both algorithm. And how is the implementation and experimentation, where we outline the engine's development and performance metrics. Well, this is like the same of like the previous videos. Well, the data exhibits concentrations of experience among developers, primarily to 2 to 20 years, while a notable peak is reserved at 10 years, suggesting a common career stage where developers might seek new opportunities. Our dataset shows predominance of full stack developers, followed by back-end developers, which reflects current industry trends. Prominence of these roles could influence our recommendation engine to favor candidates suited for these positions. Well, this is what we have been talking about the metrics that we see here. As the model metrics, the LLS demonstrates a significant reductions in error as the number of factors increase, which indicates a better fit for our data with more complex models. And the downward trends in both MA and MSC suggest that the LLS model effectively approach the underlying patterns of the data as it becomes more nuanced. And while in contrast, the gradient descent does not exhibit the same level of error reductions, possibly due to randomized starting point used in the algorithm, like I said previously. This could indicate for the given dataset and problems, gradation may not be as effective in capturing complexity of candidate and job matching. Well, if you're trying to retrain the gradation model, you will receive the different model, you will receive the different MAE and MSE metrics again. So it's really not that producible or a producible model for this kind of project that we use. Well, this is the simulation of our tactile recommendation engine. Well, we choose the age range, work arrangements, education levels of our candidates, the roles we want, and the years of experience that we want. And then we choose the candidate's technical skills, programming language like Python, or database they have been using like MongoDB, MySQL, PostgreSQL, Elasticsearch, and then cloud platforms, Amazon, Cloudflare, Google Cloud, DigitalOcean, web frameworks if you're looking for developers, or well, the scientists sometimes using frameworks, website frameworks too, but well, other frameworks like Pandas, Scikit-learn, TensorFlow, PyTorch, developer tools like what Pip, or maybe the other developer environments like Jupyter Notebook or maybe IPython and so on, RStudio, Visual Studio Code, and so on. And then the next is the operating system like Ubuntu, Windows, or maybe WSL, SL, Windows subsystem or Linux. And collaboration tools, it depends on like your if your company use that tools, you can somehow like recommend these tools for the candidates to have. And communication tools, what you're using in your companies, Google Meet, Google Chat. And when you click the recommend button, the model will return the recommended tech talent that suits or have the greatest similarity to your needs. Like, yeah, this one. Well, since our data is really skewed towards full stack and back end engineers, back end developers, that's why most of the recommendations will most likely recommend those two roles. But don't worry, as long as you can have the requirements specified, you can get the recommendation correct. All right, the next one is the conclusion and feature works, where we see the summary and feature plans or and the first one is the conclusions, where we have created engine creations, develop a cutting-edge tech talent recommendation engine to streamline HR process, data utilization, where we leverage the comprehensive Stack Overflow annual developer survey 2023 for our data-driven insights, and the library development, where we built an in-house ML from scratch library to facilitate custom matrix factorization techniques, and the algorithm iteration, where we refine recommendation logic by iterating between ALS and gradient descent algorithm, and the system integrations, where we establish a full stack solution with both front end interaction and back end processing. Containerization, where they employ Docker to containerize the applications and ensuring ease of development and scalability. And the feature works, of course, where we seek Future expansions aim to incorporate additional features to capture a wider spectrum of candidate attributes. Dataset enhancements, of course, where we seek out richer datasets for deeper insight and more precise recommendation capabilities. Model evolution, where we explore cutting-edge modeling techniques for enhanced predictive accuracy. And library upgradation, where we plan to continuous improvement of the ML from scratch, of course, for product algorithmic application. And the last one is the UI refinement, where we commit to improving the user interface for an optimal user experience. Thank you. Feel free to ask for any questions. And this is the project link of this project. See you on the next video. Bye bye.